Welcome to the sleepy Cosmoz, your peaceful gateway to the universe. Here, science meets serenity, and every journey through the cosmos is designed to calm your mind and guide you into restful sleep. If you enjoy drifting through space with us, don't forget to like this video. Our target is just 500 likes, and subscribe so you can always be part of the sleepy Cosmos family. Have you ever wondered, in the quiet hours of night, what space and time really are? Not just the ticking of a clock or the open stretch of the sky above, but the true nature of reality itself, the invisible tapestry in which every star, planet, and moment is stitched like threads in an endless cosmic quilt. Tonight, let's embark on a gentle journey to unravel the mysteries behind these profound concepts, moving slowly and thoughtfully through ideas that have fascinated thinkers for centuries. Take a deep breath, let your mind relax, and allow yourself to drift on the gentle current of wonder and curiosity as we explore the beautiful interplay of space and time. Elements as old as the universe, yet as present and intimate as your next heartbeat. Space. Most of us picture it as a kind of grand stage, a vast emptiness waiting to be filled by planets, stars, people, and possibility. It feels infinite, simple, and quietly majestic. Stretch out your hand, and space is there, embracing fingertips and thoughts alike. For ages, humans saw it as nothing more than the silent container for everything else. The endless vacuum surrounding all objects, ready to be measured, mapped, and crossed. Early philosophers even debated its very existence. Some said space was a real thing, as tangible as a bowl holding fruit. Others insisted it was a mental trick, a category in our imagination, created so we could talk about locations and movement. It wasn't until the scientific revolution that clearer explanations began to emerge, slowly painting space as something real, a backdrop for the laws of physics to unfold their magic. Isaac Newton imagined space as a kind of sacred geometry, a fixed box, stretching endlessly in every direction, unchanged no matter where you stood or which way you ran. Space, in Newton's cosmos, was absolute. It existed independently of the things moving inside it, and its measurements, locations, and distances were the same for everyone, everywhere. You could pluck an apple from the air or watch a planet glide across the sky, and space would always be there, dependable and eternal, framing each event with the precision of geometry. For centuries, this view held sway, thanks to Newton's elegant equations and unerring confidence. Scientists could predict the motion of objects, from cannonballs to comets, by plugging them into the coordinate grid of absolute space. Even time, in Newton's universe, ticked away with perfect regularity. A universal clock, impartial and inexorable, measuring out the rhythm of the cosmos. But as our nights filled with new observations, strange patterns in the behavior of light, mysterious delays in the ticking of clocks moving near the speed of those radiant beams, cracks began to form in the sturdy walls of Newton's reality. The absolute began to look more relative, the container more like a partner in the cosmic dance. The scientific stage was set for a revolution not only in physics, but in our very understanding of existence. Enter Albert Einstein, a gentle soul with wild hair and a deep sense of wonder, quietly scribbling equations that would change the world. Einstein saw space and time not as separate entities, but as lovers, intertwined, inseparable, forming a single fabric that stretches and flexes with every pulse of energy, every mass and motion in the universe. He called this unity spacetime, a four-dimensional tapestry where location and duration blend together into something more beautiful and mysterious than anyone had guessed before. Imagine space not as an empty box, but as a living ocean, its currents shaped by the planets and stars drifting within it, folding back upon itself when heavy objects like suns and black holes stir its depths. When you walk across a room, you aren't just moving through space. You're traversing space-time, following the natural contours carved by the mass of the Earth and the gentle tug of gravity. When you sleep through the night, time flows for you differently than for someone racing aboard a spaceship across the stars. Consider a simple moment. You look at the clock. You see the hands move. You feel the world change. But if you were on a fast-moving train, the passage of time would shift ever so slightly. Seconds would dilate, stretching longer for you than for those standing still. This isn't fantasy or science fiction. It's measured fact, demonstrated by precise experiments carried out over decades. Space and time, in Einstein's vision, flex and respond to movement, to energy, to gravity itself. The faster you move, the slower time passes for you, the stronger the gravitational pull. Say near a planet or deep inside a black hole, the more time stretches out, creeping by at different rates for different travelers. The universe is not static, but alive and dynamic, whispering its secrets through the movement of clocks and the shifting of distances. Space-time isn't just a fancy word for a new kind of geometry. It's a profound recognition that existence itself is built on unity. Location and duration are simply slices of a deeper reality. In this sense, every event, from the flutter of a butterfly's wings to the collision of distant galaxies, is recorded not merely in space or time, but woven into the fabric of space-time. The geography and history of the cosmos are bound together in this four-dimensional texture. When physicists talk of coordinates, they don't just mean where something happens, but when as well. The address of every event in the universe begins with four numbers: 3 for location, 1 for time. Every place has its moment, every moment its unique place. Take a moment to notice the comfort in that thought. Wherever you are, whatever you're experiencing, you are stitched into space-time as surely as any star or planet. Your memories, dreams, and hopes, even your sleep, right now, as you listen and relax, find their home within the cosmic fabric. Space does not exist apart from you. It responds to your presence. Time does not tick away beyond your reach. It carries you gently from one moment to the next, threading together the story of your life. Even as you drift into relaxation, you are part of space-time's enormous embrace. Yet, the story grows even richer when we realize that space-time itself can bend and curl. Mass and energy act upon space-time like weights upon a taut blanket, deforming its surface and changing the pathways available to anything moving nearby. When Earth circles the Sun, it's not tugged by an invisible force across empty space. It is gliding along the curved ridge of space-time created by the Sun's mass. Gravity, in Einstein's tapestry, is not a force, but a feature of geometry, a natural consequence of space-time's flexibility and depth. The classic ball and sheet analogy, used by so many physicists to describe gravity, only scratches the surface of this awe-inspiring reality. Picture the night sky. Distant light from stars bends as it passes near massive objects, its path altered not by collisions or obstacles, but by the smooth curvature of space-time itself. At the smallest scales, space-time seems continuous and gentle. But move to the extremes, approach the edge of a black hole, or the earliest instant of the universe's birth, and the fabric becomes wild, puzzling, even unpredictable. Here, space and time aren't smooth anymore. They ripple, fluctuate, and perhaps break apart into something new. Scientists call this the quantum realm, a place where uncertainty rules, and the fundamental unity of space-time reveals new secrets and surprises. It's possible, some speculate, that space-time is not truly continuous, but composed of minuscule atoms, tiny grains, smaller than anything we can now measure, which stitch together to form the illusion of a smooth and endless continuum. But tonight, let's keep our journey gentle and tranquil, letting each idea settle softly into the fabric of imagination. In our everyday lives, space and time are experienced as comfortingly stable, quietly carrying us through the dance of days and the wide arms of night. As you breathe slowly and deeply, notice how your senses reach out through space, how your awareness flows along time's gentle current. Both are partners in the story, not just the background, but living, shaping, and holding every experience, every dream, and every sleep. So, what truly is space and time? They are the most fundamental features of our universe, yet also the most mysterious. They are the infinite field upon which matter and energy play, yet they are woven together in a dance even the stars can't escape. Newton's vision gave us the rules for motion, the certainty of absolute frames. Einstein's revolution showed us the intimacy and flexibility hiding beneath the surface, a continuous, dancing, and changing tapestry shaped by the tones of gravity and the music of light. Reality is not simply laid out upon a static stage. The stage itself is alive, flexible, and deeply connected to all it contains. Tonight, as you listen and drift closer to sleep, remember that you are held in the gentle arms of space-time, woven into its fabric, along with the galaxies, stars, and everything that is, was, and ever will be. You are not separate from the universe. You are part of its core symmetry and beauty, a note in space-time's endless and soothing melody. With each breath, each heartbeat, each moment, space and time gently cradle your existence. You are at home within them, always. And as your thoughts grow softer, as night deepens around you, let these ideas comfort you. Even the vastness of the cosmos is a gentle friend, quietly unfolding around you, carrying you from one peaceful moment to the next. Let's close our eyes and drift even deeper, all the way back to a time before time, a moment so mysterious, so distant, it sits at the boundary of comprehension and wonder. Tonight's journey carries us to the birth of space-time, the origin of everything, to the event known as the Big Bang, a cosmic awakening that whispers to us through the delicate glow of distant stars and the hum in the space between atoms. Allow the rhythm of your breath to slow and let your mind wander backwards through the quiet corridors of history, past every memory, past the formation of galaxies, past even the swirling clouds of the young Earth, until there is nothing but a profound silence brimming with the potential for everything. Imagine total darkness and stillness, not just the absence of light, but the absence of anything at all. No space, no time, no before, no after. In that indescribable void, we reach what scientists call the initial singularity, a point smaller than a molecule, containing the seeds of all the stars, galaxies, and moments to come. The universe as we know it wasn't born into an existing stage. It became the stage itself. It was a moment that unfolded from pure mystery, bursting into existence not within space, but as space, bringing time itself along for the ride, a beginning that redefined beginnings. With unimaginable energy and density, the singularity expanded in an instant, a process called the Big Bang. But the term bang can be misleading. There was no explosion within an empty room. Instead, the very room itself stretched faster than the speed of light, carrying every atom, every photon, every possibility into existence. This expansion marked the genesis of both space and time, and it set the laws of physics and the cosmic clock ticking in a rhythm that would echo through the ages. For a fleeting fraction of a second, the universe went through a period called cosmic inflation, a mind-boggling transformation where the universe expanded exponentially, doubling and redoubling in size so quickly that swirls and quantum ripples became the first blueprints of galaxies. Picture a balloon, smooth and small, suddenly filled with mysterious currents that stretch its surface outward in every direction. These fluctuations, caused by quantum phenomena, may have determined where galaxies would form, where clusters would gather, and where emptiness would reign, a cosmic recipe written in the language of randomness and probability. As your thoughts drift and you sink into the comfort of night, consider that before this cosmic birth, even the very question, "What came before?" loses meaning. There was no before in any sense familiar to us, for time itself began alongside space. Our everyday intuition struggles here. We want to imagine a clock ticking, counting down to the Big Bang, but clock and countdown did not exist. The concept of before is a product of time, and time began with the expansion, leaving only mystery and awe as silent companions to the story. As the universe grew in those first moments, conditions shifted rapidly. The temperature dropped, particles emerged, and energy transformed into matter. Quarks and electrons, the elementary particles that build everything you know, sprang up out of energy fields, pairing and interacting, forming atoms that would eventually gather into stars. Just fractions of seconds later, the universe hummed with the new ingredients of reality, still unimaginably hot, but now alive with structure and possibility. The expansion did not stop there. It slowed, cooled, and eventually settled into a rhythm that would allow the formation of atoms, then clouds, then galaxies. Everything familiar was now possible. Light could travel freely through space for the very first time, leaving a faint glow that became the cosmic microwave background. A silent message from the earliest moments, still visible today to astronomers as a whisper from our universe's childhood. Take a moment to picture this, the very space filling your room, the moments ticking quietly towards sleep, the atoms swirling in distant stars. None existed before the Big Bang. Space is not a void left behind after cosmic objects depart. It is a living fabric woven as the universe grows. Time is not a river flowing on an ancient landscape. It is the landscape itself, springing forth with every new moment created by the expanding cosmos. As your eyes rest and the world outside fades, you are lying gently on the surface of space-time, born in that one cosmic exhale billions of years ago. What fills the darkness between galaxies today, those immense stretches of apparent nothingness, is a reminder of the universe's birth. Empty space is not truly empty. It vibrates with quantum energy. It expands, it shifts, and it shimmers with possibility. Scientists call it the vacuum, but it is alive with fields and fleeting particles, popping in and out of existence even as you sleep. The entire cosmic arena, from the tiniest atom to the farthest galaxy, is built on this restless, creative emptiness, a heritage from the Big Bang and inflation, preserved in every corner of spacetime. Modern telescopes and satellites scan the sky for this ancient evidence. The cosmic microwave background, that faint hum of old light, reveals a nearly perfect uniformity punctuated by gentle ripples, remnants of the quantum fluctuations during inflation. These ripples are the fingerprints of creation, telling us how galaxies grew, how matter clumped together to form stars, planets, and ultimately the atoms in your body and mind. The photons in this background have been traveling for almost 14 billion years, passing through the birth and death of generations of stars, whispering stories of the universe's earliest days. As the universe grew, so did its complexity. In only a few 100,000 years, hydrogen and helium atoms formed, and soon the first stars flickered into light. Around those stars, gravity pulled gas and dust, assembling galaxies and shaping the architecture of the universe. The slow waltz of creation continued, folding old matter into new forms, igniting supernovae, mixing elements and molecules through spaces vast and silent. Every breath you take tonight, every atom that carries your thought, was forged in these slow-burning furnaces, a testament to the endurance and creativity of space-time itself. Step back one more time in imagination to reflect on what scientists and philosophers ask about this miraculous birth. Is the universe a one-time event, a singular beginning, or one of many? Some cosmic theories propose that our universe may be one bubble in a great cosmic foam, where countless other universes expand and grow, each with its own rules and its own version of space and time. In this picture, the birth of space-time is not a unique miracle, but part of an infinite story, an endless symphony of creation and possibility. Even if we cannot see those other universes, their possibility opens the door to new dreams, new ideas, and the gentle comfort that our universe is not alone. Every effort to understand the birth of spacetime asks not just how, but why. Why was the universe born this way? Smooth, uniform, filled with the conditions for life, consciousness, and discovery. Why do its rules allow atoms to combine, stars to shine, thought to flourish, and sleep to bring comfort? Science provides the equations and the data, but the sense of wonder, the gentle awe, remains always at the edge of sleep, as much a part of us as atoms and memory. Tonight, as you listen to this gentle unfolding of the universe's birth, imagine yourself floating softly through the cosmic ocean, carried by waves of energy and possibility. The vastness above is not cold or empty, but full of memory and promise. The present moment, the room that holds you, the air that soothes you, is woven from the events of that first instant, shaped by quantum ripples and cosmic expansion. Lying awake or drifting into rest, you are part of the fabric of space-time born in the Big Bang, an unbroken chain stretching across 14 billion years, linking you with every star and every whisper of light. The story of space-time's birth is not merely for scientists or philosophers. It is a story for all of us, a lullaby written over epochs, sung in the light of distant stars, carried by every breath and every hope. The universe began not with a bang, but with a whisper, a gentle beginning that echoes still in every corner, reminding us that existence itself is an ongoing miracle. So, as sleep draws near and the night deepens around you, hold close the simple joy of knowing where you came from, knowing that all of space and time sprang into being, together, in a single act of infinite creativity, an act that continues right now with every passing moment, every flicker of thought, and every beat of your heart. Let's begin another gentle journey, floating comfortably into the heart of the space-time tapestry and its most profound transformation. Einstein's extraordinary revolution, an awakening of science and philosophy that forever changed not only the way we measure motion or observe the stars, but the very way we experience our existence each moment. As you settle back, close your eyes and breathe slowly. Let this unfolding story carry you effortlessly into a world where space bends, time stretches, and reality itself takes on new meaning. Embrace the quiet, the comfort of night. Each sentence will guide you calmly as we unravel the wonders that show spacetime's astonishing flexibility, all as revealed by Albert Einstein. Imagine the calm rhythm of life before this revolution. People step across rooms, ships journey over seas, planets orbit the sun. The rules are simple, familiar, practical, the kind described by Newton, painting the cosmos as a graceful clock with absolute coordinates and unwavering time. You could chart your way across oceans or plot the motion of comets. The equations would always fit, and the universe's unfolding seemed as predictable as dawn after a long night. But then, a slow whisper of uncertainty started drifting through the scientific world, softly unsettling old certainties. Strange experiments revealed peculiar truths about light, the way its speed always remains constant, how clocks in motion behave differently than those at rest, how the ticking itself can warp and change when subjected to light's relentless march. These clues were subtle at first, a puzzle piece here, an odd result there. But together, they hinted at something extraordinary lurking beneath reality's surface, waiting to be discovered. Albert Einstein, filled with patience and wonder, began to listen carefully to these whispers. His approach was one of gentle curiosity, questioning every assumption, ready to unravel the fabric of understanding if the evidence required it. Through years of quiet reflection, he gathered the threads of those puzzles, weaving a story that would forever shift the ground beneath our feet. Einstein's work revealed that space and time are not isolated, rigid frames, but are more like fluid partners in an endless dance. In his special theory of relativity, he showed that the speed of light is not just a physical constant, but the ultimate speed limit for all motion, a cosmic speed that nothing can surpass, no matter how hard one tries. This simple truth led to profound consequences. Time itself becomes relative, stretching or contracting depending on how fast you travel, or the strength of the gravitational field you encounter. Picture, for a moment, two twins. One remains home on Earth, relaxed in the gentle gravity, while the other embarks on a journey through the stars, racing near the speed of light. When the traveling twin returns after many years, they are younger than their earthbound sibling. The journey through space distorted time, causing it to pass differently in each frame of reference. This is not mere theory, but reality verified by countless experiments using atomic clocks, satellites, and high-speed particles. Every time an astronaut circles the planet, every time a satellite orbits above us, they slip quietly through these relativistic effects, the ticking of their clocks drifting ever so slightly from the ones back on Earth. Special relativity's consequences extend even further. Distances shrink as you race faster, objects flatten in their direction of motion, and energies grow enormous as speeds climb toward light. These phenomena bring the cosmos alive, showing us motion and rest not as categories, but as relative states, unique to each observer's journey through spacetime. But Einstein's revolution didn't stop with special relativity. The question remained, how does gravity, the gentle pull that keeps us on Earth and guides planets through space, fit into this new, dynamic picture? The answer unfurled in the general theory of relativity, an idea so beautiful and transformative that it still shapes our understanding of reality today. Einstein realized gravity is not a force transmitted invisibly between objects, but a direct consequence of spacetime's geometry. Anything with mass, from the fragile atom to monumental stars, bends the surface of spacetime itself, creating curves and ripples that change the pathways objects must follow. Imagine spacetime as a vast, elastic blanket. When a heavy object sits upon it, the surface sags, and anything nearby will roll gently toward the center, following the natural contour created by mass and energy. This picture, simple and serene, offers endless power for explaining nature's wonders. The planets move not because of a mysterious pull through empty space, but because they glide along the gentle curves created by the sun's presence. The moon orbits the Earth, held not only by invisible force, but by the natural geometry of spacetime itself, shaped uniquely by each world's mass. The implications of general relativity reach even the tranquil reaches of your nightly thoughts. Time itself, once considered absolute and steady, is revealed to be variable, responsive to gravity. The closer a clock sits to a massive object, a mountain, a planet, a black hole, the slower it ticks. Clocks on mountaintops run ever so slightly faster than those in valleys. Even your head ages marginally quicker than your toes, as the Earth's gravity ever so softly slows time throughout your body. Gravity, then, is a sculptor, shaping the flow of time, the arc of light, the motion of all things. Its artistry can be observed in the bending starlight passing near distant suns, in the spiraling motion of galaxies, and, most famously, in the astonishing phenomenon of gravitational waves. These ripples in spacetime, predicted by Einstein, are created by colossal events such as exploding stars or merging black holes. And though unimaginably faint, these waves have been detected passing gently through our solar system, causing spacetime itself to stretch and compress ever so slightly. A cosmic music audible only to the most sensitive instruments. These discoveries didn't just change science, they changed philosophy. Reality itself became more flexible, more alive, more mysterious. The notions of now and here lost their universal meaning. Each observer's experience of time and place is unique, shaped by their motion and the gravitational tide swirling through the cosmos. The universe grew richer and more interconnected. Every movement, every mass, every beam of light influences the fabric of space and time for every other part of creation. General relativity also gifted us new enigmas to explore. What happens near a black hole, where gravity bends space-time to its breaking point? What lies inside the unreachable horizon, where light and information can never return? Philosophers ponder if time has meaning in such places, where the passage of events is unlike anywhere else in the universe. These are the mysteries where Einstein's equations guide us, but where even deeper truths await, perhaps in future revolutions of science and thought. Tonight, as you let your mind drift and your body relax, all these amazing truths surround you quietly. The ground beneath, the sky above, even the gentle ticking of your heart. They all move in rhythm with space-time's curves, shaped by Einstein's astonishing vision. Every breath, every movement through your room, every night spent wondering at distant stars is touched by this intimate choreography, a dance where space and time bend, stretch, and embrace, making every moment truly unique. Einstein's theories are not just pages in a physics textbook, but companions on every journey. They guide the GPS satellites above, keeping track of time so you may find your way on Earth. They help astronomers peer back into time's depths, searching for novas and black holes across the cosmic sea. These ideas shape technology, philosophy, and the way we dream about our place in reality. Let these thoughts be gentle companions as you slip into sleep. A reminder that reality is not rigid, but flexible, not isolated, but deeply woven together. The relativity of time means each night's rest is unique. Each morning arrives in its own subtle way. You are part of space-time's beautiful dynamism, carried forward on the soft curve of the universe's unfolding story. So, as the night deepens around you, embrace the comfort of Einstein's revolution. Know that you are at home in space-time's tender embrace, unique and cherished within creation's endless beauty. The clocks may tick and the stars may spin, but your place in the cosmic dance remains utterly singular, a note in the grand melody of relativity and wonder, echoing softly as you drift into peaceful sleep. Let everything grow quiet and cozy as we slip deeper into tonight's cosmic journey. So far, we've crossed the mysteries of space and time, seen their miraculous birth, and floated serenely through Einstein's revolution. Now, let your thoughts settle, your body relax, and your imagination wander gently into one of the universe's most haunting riddles, the arrow of time. What is it, truly, that makes yesterday a memory, but tomorrow a mystery? Why does time flow in one direction, carrying us forward from birth to dream to the soft comfort of sleep? Tonight, we will unravel this secret together, moving calmly and kindly through the ideas that shape your experience, your stories, and the gentle rhythm of every heartbeat. Begin by noticing how natural it feels to think of time as a river, always flowing, always moving forward. You wake up, you eat breakfast, you watch the steady ticking of the clock move you through your day, each moment gone as soon as it arrives. But within physics, especially at the level of atoms and tiny particles, the laws of nature don't seem to care which direction time moves. Spin the hands of a mathematical clock backward, and the equations describing how electrons or photons interact still work, almost perfectly. There's a symmetry in the universe's rules, a quiet balance, like the hush between breaths. Yet, your life is different. You remember the past, you imagine the future, and every process around you, the cooling of tea, the slow fading of sunlight, happens only in one direction. What creates this difference? For centuries, scientists and philosophers have been gently tugging at the threads of this mystery, searching for what gives time its arrow, that unbroken line tracing from before to after. The answer, soothing in its elegance, rests in the strange and beautiful concept of entropy. This word, so common in science, simply describes the measure of disorder, the amount of chaos or randomness in the universe. When you mix cream into coffee, for example, the swirling dance quickly becomes a uniform blend, and the order of the separate ingredients disappears. This increase in disorder over time, so natural and inevitable, is called the second law of thermodynamics. In short, entropy always increases, and with it, time always moves forward. This law does not just shape the cooling of your midnight tea, but the entire history of the universe. After the Big Bang, the cosmos began in an incredibly low entropy state, hot, dense, uniform, full of potential. As stars formed, galaxies spun, and atoms danced into complexity, entropy grew, creating the cosmic tapestry we see today. More chaotic, more layered, filled with room for dreams and memory. The quiet comfort of entropy gives time its arrow, letting you remember your childhood and dream softly of tomorrow. Even so, this rule leaves behind gentle puzzles. Why did the universe start in a low entropy state? Why do physical processes allow reversibility in their deepest levels, but life unfolds with a clear past and future? Physicists ponder these questions as calmly as the stars ponder darkness, searching for a deeper harmony in the rules. Some say the universe's expansion itself is key. The growth of cosmic space allows entropy to increase, creating room for events to unfold in a single direction. Now, let your thoughts wander to the delicate question of memory. We live, we learn, we remember, but never in perfect symmetry. Every memory exists because your brain forms patterns, etches connections that store information about past moments. Creating these memories isn't free. It increases entropy in tiny, essential ways. A gentle payment to the universe for the privilege of experience. Your memories are low entropy treasures, made possible because the world around you grows in its complexity and possibility. Time's arrow is woven through every story, every hope, every gentle tick of the clock as you drift into sleep. That's why the songs and stories of childhood always carry an air of nostalgia, the comfort of knowing that what happened yesterday shapes today, giving meaning to each new morning and each restful night. Time's direction isn't just a physical rule. It's the melody that underpins every emotion and every dream, trustworthy and soothing as your slow breathing. Let's gently layer in one of physics's more startling facts. At a deep level, nothing in the laws of quantum mechanics or relativity strictly forbids time from running backward. In principle, the universe could unfold in reverse, with heat flowing from cold to hot, and broken glasses reassembling themselves on dinner tables. Yet, the odds of this happening are so tiny as to be impossible in practice. The universe's vast complexity, its huge number of atoms, guarantees that disorder will always spread, that the arrow of time will always point gently forward. That leads us to the tantalizing question: is time travel possible? Physicists have wondered about this with all the curiosity of poets and philosophers, exploring whether the rhythms of space and time could ever allow someone to visit their own past or leap forward into futures still unwritten. Einstein's equations permit strange objects called closed time-like curves, twisting paths through spacetime where past and future meet and loop. The concept of a wormhole, a tunnel joining distant places and moments, has inspired storytellers and scientists alike. Yet even in these beautiful visions, paradoxes lurk. The grandfather paradox, the mystery of causality, the challenge of free will and consistency. Gentle voices in science suggest that time travel may be impossible, not due to the laws of relativity, but because the universe protects its own logic. There may be deep rules, still unknown, that preserve the unbreakable arrow of cause and effect, ensuring that sleep always follows waking, and dawn always follows night. Even if time travel remains an idea for dreams, the comfort lies in knowing that the universe's order is a safe lullaby, protecting the drift from before to after. As we consider these mysteries, let's turn softly to the quantum world, where time shows even stranger facets. At this level, particles flicker in and out of possibility, sometimes appearing to ignore the arrow of time, sometimes unfolding in ways that seem almost magical. Some interpretations suggest that the collapse of quantum states, the moment when pure potential becomes certain reality, imposes its own arrow, giving the future a unique profile with every measurement. Does consciousness play a role in shaping the flow of time? Does reality split with every new choice, branching into parallel worlds where different stories unfold? These are gentle questions for another night, but tonight, let them settle quietly, allowing the peace of sleep to carry you onward. Look for the cosmological arrow, the direction pointed by the universe's expansion. Since the Big Bang, space has grown bigger, carrying galaxies farther apart, stretching everything gently, calmly into the future. That's another reason tomorrow is always different from yesterday. The fabric you rest upon tonight is more expansive than it was the day before, offering a universe just a little bigger, a little richer with each passing moment. Tonight, everything, from the rise and fall of your breath to the swirling clouds and distant galaxies, is built on this arrow, a soft assurance that time moves forward, that each experience is stitched into a tapestry that only grows. Rest in the knowledge that even as the deepest laws of physics invite speculation, the comfort of entropy, the certainty of memory, and the gentle promise of tomorrow are always with you. As you listen to the quiet, unfolding of time's arrow, let worries about reversibility, paradox, or disorder dissolve into the tranquility of the night. The universe's harmony is deep and resilient, a lullaby for every sleeping star and waking mind. Time moves forward, carrying you gently, safely, toward dreams and renewal. In your nightly rest, you share a journey not just with the people of today, but with all the moments of the universe, a voyage from the low entropy dawn of creation to the promise of futures still to come. Take comfort in this, knowing that the direction of time is the oldest, most soothing melody, as ancient as the first light, as sure as the hope in every new day. Let sleep come softly now, with the renewed understanding that time's journey is as gentle and inevitable as the darkening sky. You are cradled in its flow, a cherished traveler in the boundless universe, a keeper of memories, a dreamer of mornings yet to arrive. Time's arrow points you ever forward. Rest easy in its promise and beauty. Close your eyes and let your mind drift even deeper into the cosmos tonight as we venture into the most mysterious and beautiful realm of all, the quantum world, where the very foundations of reality become soft, uncertain, and wonderfully strange. Here, in the gentle embrace of night, we'll explore how the smallest particles in the universe dance in ways that challenge everything we think we know about existence, space, and time. Let your breathing slow, your thoughts settle, and your imagination float freely as we uncover the quantum secrets that weave through every atom in your body, every photon of starlight, and every moment of this peaceful evening. In the world we see and touch each day, everything seems solid, predictable, and reassuringly real. Chairs remain chairs, walls stay walls, and the moon follows its reliable path across the sky. But venture down into the microscopic realm, smaller than cells, smaller than atoms, into the quantum domain where the building blocks of reality reside. And suddenly, the rules change in the most enchanting ways. Here, Particles don't have definite positions until someone looks for them. They exist in multiple states simultaneously, like ghostly possibilities waiting to be discovered. They can tunnel through barriers that should be impossible to cross, and they can be mysteriously connected across vast distances in ways that Einstein once called spooky action at a distance. This quantum realm isn't separate from your everyday experience. It's the foundation upon which your entire world rests. Every breath you take, every thought that crosses your mind as you drift toward sleep, every gentle beat of your heart depends on quantum processes unfolding in countless billions of atoms. The very act of seeing, of hearing these words, relies on photons, particles of light that exist as both waves and particles until the moment they reach your eyes and collapse into the specific reality you perceive. Let's begin with one of quantum mechanics' most beautiful mysteries: superposition. Imagine a particle, perhaps an electron, spinning around an atomic nucleus that doesn't just spin in one direction or another, but exists in a graceful combination of all possible spins at once. This isn't because we don't know which way it's spinning. It's because the electron truly exists in multiple states simultaneously, like a cosmic symphony playing all its notes at the same time. Only when we measure the electron, when we observe it with our instruments, does it choose a single state, collapsing from infinite possibility into one specific reality. This quantum behavior extends to position and momentum as well. Particles don't follow defined paths through space like tiny billiard balls. Instead, they exist as clouds of probability, spread across all the places they might be found. Heisenberg's uncertainty principle tells us that we can never know both where a particle is and where it's going with perfect accuracy. The more precisely we pin down one property, the more uncertain the other becomes. This isn't a limitation of our measuring tools. It's a fundamental feature of reality itself, a gentle reminder that at its deepest level, the universe preserves an element of mystery and possibility. Perhaps even more wondrous is the phenomenon of quantum entanglement, where two or more particles become connected in ways that seem to transcend space and time. When particles become entangled, measuring one instantly affects the other, regardless of how far apart they may be. If you measure the spin of one entangled electron and find it spinning clockwise, you instantly know its partner is spinning counterclockwise, even if it's on the other side of the galaxy. This connection isn't caused by any signal traveling between them. It's as if the particles remain part of a single, unified system, sharing a quantum destiny that Einstein found deeply troubling, but that experiments have confirmed beyond doubt. This quantum entanglement reveals something profound about the nature of spacetime itself. The classical view of locality, that objects can only influence their immediate neighbors, begins to blur in the quantum world. Information about quantum correlations seems to exist outside the normal flow of space and time, suggesting that at the deepest level, the universe is more intimately connected than our everyday experience would suggest. Every quantum measurement, every collapse of a wave function, ripples through the fabric of reality in ways we're only beginning to understand. The marriage of quantum mechanics and relativity creates even deeper mysteries. In Einstein's universe, space-time is smooth and continuous, a gentle fabric that curves around massive objects. But quantum mechanics suggests that at the smallest scales, the Planck length, about a billion times smaller than an atom, space-time itself might become granular, uncertain and subject to quantum fluctuations. Picture the smooth surface of a calm ocean that, when viewed through a powerful microscope, reveals itself to be made of constantly churning water molecules. Similarly, the space-time that seems so stable and reliable might, at its foundation, be a seething foam of quantum possibilities. This quantum foam, as physicists call it, represents the marriage of space, time, and uncertainty. Virtual particles pop into existence and annihilate each other in tiny fractions of a second, borrowing energy from the vacuum itself before paying it back. These quantum fluctuations aren't just theoretical curiosities. They have measurable effects, subtly influencing the behavior of atoms and the structure of spacetime. The empty space around you as you rest tonight is actually alive with this quantum activity, a gentle dance of creation and destruction happening at scales far too small to perceive, but fundamental to the very existence of reality. One of the most profound questions in quantum mechanics concerns the role of measurement and observation. Why does a quantum system, existing in multiple states simultaneously, suddenly choose one specific outcome when observed? This measurement problem touches on deep philosophical questions about the nature of consciousness and reality. Some interpretations suggest that consciousness plays a fundamental role in collapsing quantum superpositions, that the act of observation by a conscious being is necessary to transform quantum possibilities into definite reality. Others propose that the universe constantly splits into parallel branches, with each possible outcome playing out in its own separate reality. The many worlds interpretation paints a picture of reality that's both beautiful and mind-bending. In this view, every quantum measurement causes the universe to branch, creating parallel worlds where each possible outcome occurs. There might be countless versions of you, each experiencing slightly different quantum outcomes, all existing simultaneously in parallel branches of reality. While we can never communicate with these other versions of ourselves, the theory suggests they're just as real as the version of you listening to these words tonight, gently drifting toward sleep in this particular branch of the cosmic tree. Recent advances in quantum field theory have revealed even more subtle connections between quantum mechanics and spacetime. The vacuum itself, what we think of as empty space, is actually the lowest energy state of quantum fields that fill all of reality. These fields are constantly fluctuating, creating and destroying virtual particles, generating the quantum foam that might underlie the smooth appearance of spacetime. Some theories suggest that spacetime itself might be an emergent property of quantum entanglement, that the geometry of the universe arises from the pattern of quantum connections between its fundamental constituents. As you let these ideas wash over you, like gentle waves, remember that you're not separate from this quantum dance. Every atom in your body was forged in the nuclear furnaces of ancient stars through quantum processes. The electrons in your neurons tunnel through energy barriers in ways that classical physics says should be impossible, enabling the thoughts and dreams that define your conscious experience. The very act of listening to these words, of processing meaning from sound, depends on quantum mechanics operating within your brain and sensory organs. Tonight, as you drift into sleep, you're cradled not just by the smooth fabric of Einstein's spacetime, but by the gentle uncertainty and infinite possibility of the quantum world. Your dreams themselves might be expressions of quantum creativity, your consciousness surfing the collapsing wave functions of possibility into the specific reality of each new moment. Rest peacefully in the knowledge that you're part of this cosmic quantum symphony, a unique expression of the universe's fundamental creativity and mystery. The quantum realm reminds us that reality is far more flexible, interconnected, and beautiful than our everyday experience suggests. In this gentle uncertainty, in these invisible connections that span the cosmos, in the constant dance of possibility and actuality, we find not chaos, but a deeper harmony, a lullaby sung by the fundamental particles of creation, carrying you softly toward dreams as infinite and mysterious as the quantum cosmos itself. Let your mind drift now toward the most mysterious and awe-inspiring objects in the entire cosmos. Black holes, those cosmic giants, where the very fabric of space-time becomes so twisted and warped that our understanding of reality reaches its ultimate limits. As you settle deeper into the comfort of night, imagine journeying to the edge of one of these magnificent enigmas, where space and time themselves dance to rhythms unlike anywhere else in the universe. Tonight, we'll explore these celestial wonders with gentle curiosity, discovering how black holes challenge everything we thought we knew about existence, while offering profound insights into the deepest mysteries of space, time, and the nature of information itself. Picture a star, massive beyond imagination, perhaps 20 or 30 times heavier than our sun, reaching the end of its brilliant life after millions of years of nuclear fusion. As its fuel exhausts, the star can no longer support itself against its own immense gravity. In a catastrophic moment that lasts mere seconds, the star's core collapses, creating temperatures and pressures so extreme that not even the force holding atomic nuclei together can resist. Matter is crushed to densities beyond comprehension, and if the star is massive enough, this collapse continues beyond all known limits, creating a region of space-time so curved that not even light can escape its gravitational embrace. This is how a black hole is born, not through destruction, but through the ultimate expression of gravity's creative power. The boundary around a black hole, called the event horizon, marks the point of no return. It's not a physical surface you could touch, but rather a threshold in space-time itself, an invisible sphere where the escape velocity equals the speed of light. Once anything crosses this boundary, whether it's a photon, a spaceship, or a single atom, it can never return to the outside universe. The event horizon is like a one-way door through which matter and energy can enter, but from which no information can ever escape. From your perspective, watching safely from a distance, something remarkable happens to anything approaching a black hole. As an object falls toward the event horizon, time dilation becomes more and more extreme. You would see the falling object slow down dramatically, its image growing redder and dimmer, as the light it emits is stretched to longer and longer wavelengths. The object would appear to freeze at the event horizon, its image fading gradually until it becomes invisible, preserved forever in your reference frame at that boundary between the known and unknowable. But from the perspective of someone falling into the black hole, the experience would be entirely different. Time would continue to flow normally for them, and they would cross the event horizon without any special sensation, continuing their journey toward the center. This profound difference in perspectives, where the same event appears frozen from outside, but continues normally from within, illustrates one of the most beautiful and puzzling aspects of Einstein's relativity. Reality itself depends on where you are and how you're moving through space-time. As our imaginary traveler continues falling inward, they would eventually encounter the singularity at the black hole's center, a point where the curvature of space-time becomes infinite and the laws of physics, as we understand them, break down completely. Here, the very concepts of space and time lose their meaning. General relativity predicts that matter would be compressed to infinite density in zero volume, creating conditions that our current theories simply cannot describe. The singularity represents the ultimate frontier of human knowledge, a place where physics itself reaches its limits and new understanding awaits. Yet black holes are not just cosmic monsters that devour everything around them. Stephen Hawking discovered one of the most profound and surprising truths about these objects. They actually emit radiation and slowly evaporate over time. Through the subtle interplay of quantum mechanics and curved spacetime, particle pairs that normally appear and disappear in the quantum vacuum near the event horizon can become separated. One particle falls into the black hole, while the other escapes, carrying away a tiny amount of energy. This Hawking radiation means that black holes have temperature. They glow with a faint warmth inversely, proportional to their mass. This discovery created one of the deepest puzzles in modern physics, the information paradox. According to quantum mechanics, information cannot be destroyed. Every quantum state must be preserved in some form. But if a black hole completely evaporates through Hawking radiation, and if that radiation appears to carry no information about what fell into the black hole, then where does the information go? This question sits at the intersection of quantum mechanics, relativity, and thermodynamics, challenging our understanding of the fundamental laws that govern reality. Recent theoretical developments suggest that the information paradox might be resolved through a deeper understanding of how black holes connect to the surrounding spacetime. The holographic principle proposes that all the information falling into a black hole is actually encoded on its two-dimensional event horizon, like a hologram that contains all the information about a three-dimensional object. This radical idea suggests that what we perceive as the three-dimensional interior of a black hole might be an illusion, that all the real information exists on the boundary surface. This holographic understanding has led to even more profound insights about the nature of space-time itself. Some physicists now believe that space-time might be an emergent phenomenon, arising from the pattern of quantum entanglement between different regions of space. In this view, the smooth fabric of Einstein's spacetime that we experience is like the calm surface of a deep ocean, beneath which lies a turbulent quantum sea of entangled particles and information. Black holes also serve as natural laboratories for testing the most extreme predictions of general relativity. The recent detection of gravitational waves, ripples in spacetime itself, was achieved by observing the collision and merger of black holes. These cosmic catastrophes, occurring billions of light years away, send waves through the fabric of spacetime that we can detect here on Earth with instruments sensitive enough to measure changes smaller than 1,000th the width of a proton. Each gravitational wave detection tells us about the dance of matter and energy in the most extreme environments in the universe. Rotating black holes add another layer of complexity and wonder to these cosmic enigmas. As a black hole spins, it drags space-time around with it in a phenomenon called frame dragging. Near a rotating black hole, the very definition of standing still changes. Space itself is pulled around by the black hole's rotation. This effect creates an ergosphere around the black hole, a region where it becomes impossible to remain stationary relative to distant observers. The rotation of spacetime in this region opens up the possibility of extracting energy from the black hole itself, as first proposed by Roger Penrose. Some rotating black holes might even contain closed time-like curves, paths through spacetime that loop back to their starting point in time. While cosmic censorship hypotheses suggest that nature prevents such paradoxical situations from forming in realistic scenarios, the mathematical possibility remains a source of fascination for physicists and philosophers alike. These exotic space-time geometries challenge our understanding of causality and the nature of time itself. As you contemplate these cosmic mysteries while drifting toward sleep, remember that black holes are not just distant objects of academic interest. They play crucial roles in shaping the universe we inhabit. Supermassive black holes, millions or billions of times heavier than our Sun, reside at the centers of galaxies, including our own Milky Way. These galactic anchors help regulate star formation and the evolution of cosmic structure over billions of years. The black hole at the center of our galaxy, Sagittarius A star, has been a quiet companion to our solar system throughout its entire history. Tonight, as you rest in the gentle embrace of Earth's gravity, you're connected to these cosmic wonders through the same fundamental forces that created them. The atoms in your body were forged in stellar cores that might someday collapse into black holes. The space-time that cradles your dreams is the same fabric that bends and warps around these gravitational giants. In contemplating black holes, we glimpse not just the extreme limits of physics, but the profound unity that connects the smallest quantum fluctuations to the grandest cosmic structures. Let these thoughts of cosmic mystery and wonder carry you gently into sleep, knowing that even in a universe containing objects as extreme as black holes, there remains a fundamental harmony, a deep order that connects all things through the beautiful mathematics of spacetime. The mysteries of black holes remind us that reality is far stranger and more wonderful than we ever imagined, full of puzzles that challenge our understanding while inspiring our continued search for truth. Rest peacefully tonight, cradled by the same gravitational forces that create these cosmic wonders, part of a universe infinite in its capacity for surprise and beauty. Settle into the deepest comfort of night now, as we embark on perhaps the most mind-expanding journey of all, into the possibility that our entire universe, with all its galaxies, stars, and the very room where you rest tonight, might be just one bubble in an infinite ocean of realities. Let your thoughts drift freely as we explore the multiverse, that vast landscape of parallel worlds and alternate possibilities that stretches beyond imagination. Tonight, we'll gently navigate this cosmic archipelago of universes, each with its own laws of physics, its own history, and its own version of space and time, discovering how the very act of existing might mean sharing reality with countless other versions of everything that is, was, or ever could be. Imagine for a moment that somewhere in a universe parallel to ours, another version of you is listening to these very words. Perhaps in that world, the laws of physics are slightly different. Maybe gravity is a bit stronger, or light travels at a different speed. Perhaps that other version of you made different choices, followed different paths, experienced different dreams. The multiverse hypothesis suggests that such parallel realities don't just exist in science fiction, but might be the natural consequence of the same physical processes that created our own cosmic home. As you breathe slowly and let your mind wander, consider that your existence might be just one note in an infinite symphony of possibility. The seeds of multiverse theory grow from some of our most successful scientific ideas, beginning with the cosmic inflation that shaped our universe in its earliest moments. During that first fraction of a second after the Big Bang, space expanded exponentially, stretching quantum fluctuations into the cosmic structures we observe today. But inflation theory suggests this process doesn't stop everywhere at once. Instead, different regions of space stop inflating at different times, creating separate bubble universes within an eternally expanding multiverse. Our observable universe would be just one such bubble, surrounded by an infinite expanse of other cosmic domains, each with potentially different physics and evolution. This eternal inflation model paints a picture of endless creativity, where new universes are constantly being born as inflation ends in different regions. Each bubble universe would have its own Big Bang, its own expansion history, and its own unique properties. Some might be similar to ours, with familiar atoms, stars, and galaxies. Others might be radically different, perhaps universes where dark matter dominates completely, or where the fundamental forces combine in ways that prevent the formation of complex structures. The multiverse becomes an infinite laboratory of cosmic possibility, exploring every conceivable variation on the theme of existence. But eternal inflation is just one path to the multiverse. Quantum mechanics itself suggests another route through the many worlds interpretation, that elegant solution to the measurement problem we encountered earlier. Each time a quantum system exists in superposition, simultaneously in multiple states, and then gets measured, the universe might split into parallel branches, each containing one of the possible outcomes. The particle that could spin either up or down doesn't choose randomly. Instead, both outcomes occur, but in separate parallel universes that diverge from that moment forward. In this quantum multiverse, every decision you've ever made, every quantum event that has ever occurred, creates new branches of reality. There are universes where you chose differently at every major crossroads of your life. Universes where quantum events unfolded along different paths. Universes where the random mutations of evolution took life in entirely different directions. The version of you resting comfortably tonight exists alongside countless other versions, each experiencing their own unique trajectory through the vast space of quantum possibilities. String theory, our most ambitious attempt to unify all the forces of nature, adds yet another layer to the multiverse tapestry. This elegant theory requires extra dimensions beyond the familiar 3 of space plus 1 of time, perhaps as many as 11 dimensions in total. The way these extra dimensions curl up and fold upon themselves at each point in space determines the physics we observe. But there might be an enormous number of ways for these dimensions to fold, creating what string theorists call the landscape, a vast space of possible universes, each with different particles, forces, and constants of nature. The string landscape might contain as many as 10 to the 500 different possible universes, a number so large it defies comprehension. Each point in this landscape represents a different vacuum state, a different way the universe could exist, with different values for fundamental constants like the strength of gravity, the mass of electrons, or the rate of cosmic expansion. Our universe occupies just one point in this vast landscape, while countless other universes explore the other possibilities, creating a cosmic ensemble where every mathematically consistent set of physical laws finds expression in reality. This leads us to one of the most profound questions in cosmology. Why do the physical constants in our universe seem so perfectly tuned for the existence of stars, planets, and life? The strength of gravity, the mass of the proton, the rate of cosmic expansion, all appear to fall within narrow ranges that allow for complex chemistry and stable stellar evolution. This fine-tuning might seem to suggest design or purpose, but the multiverse offers an elegant alternative. If there are countless universes with different physical constants, then some, including ours, will naturally have values that permit complexity and life. This anthropic reasoning suggests that we observe a life-friendly universe not because it was designed that way, but because we could only evolve to ask such questions in universes where the constants permit our existence. Universes with different values might exist in vast numbers, but they remain unobserved because they cannot support observers. In this view, the apparent fine-tuning of our cosmic home becomes a selection effect rather than a cosmic coincidence, as natural and inevitable as finding yourself on a planet with water and air. Yet the multiverse raises profound philosophical questions that ripple through our understanding of meaning, uniqueness, and scientific explanation. If every possible universe exists somewhere in the multiverse, what makes any particular outcome special or meaningful? If there are infinite versions of you making every possible choice, what does individual responsibility mean? Some argue that multiverse theories are unscientific because they make predictions that cannot be tested or falsified. Others contend that the multiverse is the natural consequence of our most successful theories, emerging inevitably from quantum mechanics, inflation, and string theory. Recent developments in cosmology have begun to suggest possible ways to test multiverse theories. If our universe collided with another bubble universe in the distant past, such an encounter might leave subtle signatures in the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. Similarly, if eternal inflation is correct, it might predict specific patterns in the distribution of galaxies and the spectrum of gravitational waves. These observations could provide evidence for the reality of the multiverse, transforming it from philosophical speculation into testable science. The holographic principle, which we encountered in our exploration of black holes, adds another fascinating dimension to multiverse thinking. If the information content of any region of space can be encoded on its boundary surface, then our three-dimensional universe might be a holographic projection of information stored on a two-dimensional surface. This could mean that what we experience as parallel universes in the multiverse are actually different ways of interpreting the same underlying information, different holographic projections of a single, more fundamental reality. Some theorists even propose that consciousness itself might play a role in selecting which branch of the multiverse we experience. The quantum multiverse suggests that all possibilities exist simultaneously until observed, but conscious observation might determine which branch becomes real for a given observer. In this view, your awareness as you drift towards sleep tonight might be the factor that selects which version of tomorrow you'll wake up to experience, choosing from among countless parallel possibilities. As you contemplate these infinite landscapes of possibility, remember that whether the multiverse exists or not, your experience remains unique and precious. The consciousness that contemplates these questions, the awareness that can appreciate the beauty of parallel worlds and alternate realities, is extraordinary regardless of how many universes might exist. Your thoughts, dreams, and capacity for wonder are remarkable whether they occur in one universe or countless trillions. Tonight, let the concept of the multiverse bring comfort rather than insignificance. If there are infinite universes, then there are infinite expressions of beauty, creativity, and love. Every sunset that ever could be painted across a sky exists somewhere in the multiverse. Every song that could bring joy to a heart is being played in some parallel world. Every peaceful moment of rest, like the one you're experiencing now, is multiplied across countless realities, each one as real and meaningful as your own. Rest peacefully in the knowledge that whether our universe stands alone or swims in an ocean of parallel realities, you remain a unique and irreplaceable part of existence. The multiverse, if it exists, doesn't diminish the importance of your individual journey. It celebrates the infinite creativity of reality itself, expressing every possibility while ensuring that your particular path through space and time remains distinctly, beautifully yours. Sweet dreams tonight, knowing that in whatever number of universes you might exist, this moment of peaceful contemplation connects you to the deepest mysteries of existence itself. Let your mind drift now into perhaps the most intimate and mysterious territory of all, the relationship between consciousness and the quantum fabric of reality itself. As you settle deeper into the gentle embrace of night, we'll explore one of the most profound questions that sits at the intersection of physics and philosophy. What role does awareness, observation, and consciousness play in shaping the very nature of existence? Tonight, we'll journey through the delicate territory where mind meets matter, where the act of knowing intersects with the quantum dance of possibility, discovering how your own awareness might be far more fundamental to reality than you ever imagined. Close your eyes and consider for a moment the simple act of observation. Right now, as you listen to these words, photons of light that have traveled across space are striking objects around you, bouncing off surfaces, and entering your eyes to create the visual experience of your surroundings. But in the quantum world, this innocent act of observation takes on profound implications. According to the orthodox interpretation of quantum mechanics, particles exist in superposition, multiple states simultaneously, until the moment they are observed. The electron doesn't spin in a definite direction. The photon doesn't travel along a specific path. The quantum system doesn't occupy a particular state until consciousness encounters it, and the wave function collapses into a single, definite reality. This relationship between observation and reality creates one of the deepest puzzles in modern physics. If quantum systems exist in superposition until observed, what exactly constitutes an observation? Does it require a conscious observer, or is any interaction with a measuring device sufficient? Some interpretations suggest that consciousness plays a fundamental role in determining reality, that the universe exists in a state of quantum potentiality until mind encounters matter and transforms possibility into actuality. In this view, your awareness as you drift towards sleep tonight isn't just experiencing reality. it's actively participating in its creation. The measurement problem in quantum mechanics reveals the profound mystery at the heart of this relationship. When set up an experiment to measure a quantum property, we find that the very act of measurement seems to force the quantum system to choose one specific outcome from all the possibilities available to it. Before measurement, the system exists in what physicists call a coherent superposition, all possibilities coexisting in a delicate quantum balance. After measurement, we find one definite result, as if the universe has suddenly decided which reality to manifest. What's particularly intriguing is that different conscious observers can have different experiences of the same quantum event. In quantum mechanics, the notion of objective reality, a single, definite state of affairs that exists independent of observation, becomes deeply problematic. Instead, reality might be fundamentally relational, existing in the interactions between conscious observers and the quantum systems they encounter. Your experience of reality tonight, as you listen and relax, might be uniquely yours, constructed through the interface between your consciousness and the quantum processes in your brain and environment. This leads us to consider the hard problem of consciousness itself, the mystery of how subjective experience arises from physical processes. While neuroscience has made remarkable progress in mapping the neural correlates of consciousness, the question of why there's something it's like to be you, why you have inner subjective experience at all, remains one of the deepest mysteries in science. Some researchers propose that consciousness might be a fundamental feature of reality, like mass or charge, rather than something that emerges from complex arrangements of unconscious matter. The integrated information theory suggests that consciousness corresponds to integrated information in a system, the amount of information generated by the whole system above and beyond its parts. In this view, consciousness isn't localized to brains, but is a measure of how much a system can integrate and process information. This theory raises the intriguing possibility that quantum systems, with their vast capacity for information, processing through superposition and entanglement, might possess forms of consciousness vastly different from our own. Recent research in quantum biology reveals that quantum effects might play crucial roles in biological processes, including potentially in the operation of consciousness itself. Quantum coherence has been discovered in photosynthesis, bird navigation, and possibly even in the microtubules within neurons. Some theorists propose that consciousness might emerge from quantum processes in the brain, with quantum coherence allowing for the kind of integrated information processing that generates subjective experience. Your thoughts, as you drift toward sleep, might literally be quantum phenomena, patterns of coherence and entanglement playing out in the neural networks of your mind. The delayed choice quantum eraser experiments reveal even more mysterious connections between observation and reality. These experiments suggest that the decision about how to observe a quantum system can retroactively determine the system's past behavior. A choice made in the present can influence the path a photon took in the past, as if consciousness can reach backward through time to shape the history of quantum events. While these experiments don't allow for communication with the past, they hint at deep connections between mind, time, and reality that we're only beginning to understand. The many worlds interpretation offers a different perspective on the role of consciousness in quantum mechanics. In this view, every quantum measurement causes the universe to split into parallel branches, each containing a different outcome. Consciousness doesn't collapse the wave function. Instead, it experiences one particular branch of the ever-branching multiverse. Your awareness tracks one path through the vast tree of possibilities, while other versions of you in parallel branches experience different outcomes. In this interpretation, consciousness becomes a navigator through the quantum multiverse rather than a creator of reality. The quantum Zeno effect demonstrates another fascinating connection between observation and quantum evolution. By repeatedly observing a quantum system, you can actually slow down or even halt its natural evolution. The act of measurement can freeze a quantum system in its current state, preventing it from transitioning to other possibilities. This effect suggests that consciousness, through its power of observation, might have a subtle but real influence on the unfolding of physical processes. Your attention, as you focus on these ideas, might be gently shaping the quantum processes in your own brain and environment. Some interpretations of quantum mechanics propose that consciousness is required not just for the collapse of wave functions, but for the very existence of physical reality. In these views, the universe exists as pure information or mathematical possibility until consciousness encounters it and transforms abstract potential into concrete experience. Matter, energy, space, and time might all be manifestations of the interaction between universal consciousness and the quantum field of possibilities. You are not just in the universe. In some profound sense, the universe exists through your awareness of it. The study of near-death experiences, meditation states, and psychedelic experiences has revealed altered states of consciousness that seem to transcend ordinary space-time limitations. People report experiences of unity with the universe, perception of parallel realities, and access to information that seems impossible through normal sensory channels. While these experiences are difficult to study scientifically, they hint at the possibility that consciousness might have capacities beyond what we typically recognize, perhaps including the ability to interact directly with the quantum substrate of reality. The anthropic principle, the observation that the universe's physical constants seem fine-tuned for the existence of conscious observers, takes on new meaning when we consider consciousness as fundamental. Perhaps the universe isn't fine-tuned for consciousness by accident, but rather consciousness and cosmos co-evolve together, each shaping the other in an endless dance of mutual influence. The physical laws that govern matter and energy might themselves be expressions of deeper principles that include consciousness as a fundamental feature. As you contemplate these profound connections between mind and reality, remember that your own consciousness is perhaps the most direct access you have to the fundamental nature of existence. Every thought, every perception, every moment of awareness as you drift toward sleep is a window into the deepest mysteries of the cosmos. The fact that you can contemplate these questions at all, that the universe has evolved conscious beings capable of wondering about consciousness, is perhaps the most remarkable feature of reality. Tonight, as you rest in the gentle flow of awareness, consider that your consciousness might be more than just an observer of reality. It might be an active participant in the cosmic dance of existence. Your thoughts, dreams, and capacity for wonder are not separate from the quantum processes that govern the universe. They are expressions of those processes, consciousness experiencing itself through the unique lens of your individual awareness. In the deepest sense, You are not just conscious of the universe is conscious through you. Let these ideas carry you gently into sleep, knowing that whether consciousness shapes reality or reality shapes consciousness, or both simultaneously in some deeper dance of existence, your awareness remains a precious and irreplaceable part of the cosmic story. Rest peacefully tonight, cradled by the mysterious relationship between mind and cosmos, part of the universe contemplating itself through the miracle of conscious experience. Allow your thoughts to settle into the deepest philosophical waters now as we explore how the revolutionary discoveries of modern physics have transformed humanity's oldest questions about existence, meaning, and our place in the cosmic order. Tonight, as you drift into peaceful contemplation, we'll journey through the profound philosophical implications of everything we've discovered together, from the birth of spacetime to the mysteries of consciousness, and see how these scientific revelations illuminate eternal questions about free will, determinism, the nature of causality, and what it truly means to exist in this quantum universe. Let your mind relax completely as we weave together physics and philosophy into a gentle tapestry of understanding. Consider for a moment the ancient philosophical debate between determinism and free will, a question that has occupied human minds for millennia. Classical physics, with its clockwork precision, seemed to support a deterministic universe where every event was the inevitable result of prior causes, stretching back in an unbroken chain to the beginning of time. If you could know the position and velocity of every particle in the universe, the argument went, you could predict the entire future and retrodict the entire past. In such a universe, free will would be an illusion. Your choices tonight, your decision to listen to these words, your drift towards sleep, all predetermined by the arrangement of atoms at the dawn of creation. But quantum mechanics has fundamentally altered this picture, introducing genuine randomness into the fabric of reality. When an electron tunnels through a barrier or a radioactive atom decides to decay, these events appear to be truly random, not just unpredictable due to our ignorance, but genuinely undetermined until they occur. This quantum indeterminacy might seem to rescue free will from the grip of determinism, but it raises new puzzles. If our choices are based on random quantum events, are they truly free in any meaningful sense? Or are we simply sophisticated quantum dice, rolling toward decisions we don't control? The relationship between quantum mechanics and free will becomes even more complex when we consider the many worlds interpretation. In this view, every quantum event creates a branching of reality, with all possible outcomes occurring in parallel universes. This suggests that every choice you could make, you do make, somewhere in the vast landscape of parallel realities. There are versions of you that chose differently at every decision point, each following their own unique path through the quantum multiverse. This proliferation of possibilities raises profound questions about moral responsibility and the meaning of choice. If all possibilities are realized somewhere, what weight should we give to the particular choices we make in this branch of reality? The nature of time itself, as revealed by Einstein's relativity, adds another layer to these philosophical puzzles. If simultaneity is relative, if there's no universal now that defines the present moment for everyone, then what does it mean to say that the future is open and the past is fixed? From the perspective of space-time as a four-dimensional block, all moments, past, present, and future exist equally. Your birth, your present experience of listening to these words, and your eventual death all exist as permanent features of the space-time manifold. This eternal or block view of time suggests that becoming is an illusion, that change is just our limited perspective, moving through a static, four-dimensional landscape. Yet our subjective experience of time's flow, of genuine becoming and change, seems so fundamental to conscious existence that many philosophers argue it must reflect something real about the nature of reality. Perhaps consciousness itself creates the flow of time, selecting which moments to experience in sequence from the eternal landscape of space-time. Or perhaps time's passage is an emergent property of thermodynamics and entropy, as conscious beings like ourselves can only exist in the context of increasing disorder and information processing. The measurement problem in quantum mechanics raises profound questions about the role of observation in determining reality. If conscious observation plays a role in collapsing quantum superpositions, then observers become active participants in creating the reality they inhabit. This participatory universe, as physicist John Wheeler called it, suggests that the classical division between subject and object, observer and observed, might be a useful approximation that breaks down at the quantum level. Reality becomes a collaborative creation between conscious minds and the quantum potentialities of the physical world. This participatory view of reality resonates with ancient philosophical traditions that saw consciousness as fundamental rather than emergent. The Hindu concept of consciousness as the ground of being, the Buddhist notion of dependent origination, where phenomena arise through interconnected relationships, and various idealist philosophies all anticipated what modern physics might be discovering: that mind and matter are more intimately connected than Western thought traditionally assumed. The anthropic principle, the observation that our universe's physical constants seem remarkably fine-tuned for the existence of complexity, stars, planets, and life, raises deep questions about chance, necessity, and design. In a single universe, such fine-tuning might seem to require explanation, perhaps pointing toward purpose or intelligence in the cosmic order. But in a multiverse containing all possible variations of physical law, our life-friendly universe becomes a natural inevitability rather than an unlikely coincidence. We observe fine-tuning not because the universe was designed for us, but because we could only evolve to make observations in universes where such fine-tuning exists. This multiverse solution to fine-tuning raises its own philosophical puzzles about meaning and significance. If everything that can happen does happen somewhere in the infinite landscape of parallel realities, what makes any particular outcome special or meaningful? Some philosophers argue that infinite parallel worlds drain meaning from individual existence, while others contend that meaning remains grounded in the quality of experience rather than its uniqueness or rarity. The holographic principle suggests that reality might be fundamentally different from our three-dimensional experience, that all the information in any region of space can be encoded on its two-dimensional boundary. This challenges our intuitive understanding of what exists and what is merely appearance. If our three-dimensional world is a projection of information stored on a distant boundary, then questions about the reality of everyday objects, the nature of identity, and the relationship between appearance and truth take on new urgency. Quantum entanglement reveals that the universe is far more interconnected than classical physics suggested. When particles become entangled, they remain connected regardless of spatial separation, sharing a unity that transcends the ordinary limits of space and time. This quantum interconnectedness might provide a physical basis for philosophical concepts like universal consciousness, the interconnectedness of all beings, or the holistic nature of reality. Your existence tonight is not that of an isolated individual, but of a deeply connected node in the vast network of quantum relationships that constitute the universe. The emergence of complexity from simple rules observed throughout physics and cosmology suggests that the universe has an inherent tendency toward increasing complexity and organization. From the formation of atoms in stellar furnaces, to the evolution of biological systems, to the emergence of consciousness itself, the cosmos seems to be engaged in an ongoing creative process. This evolutionary cosmology provides a scientific framework for philosophical concepts like emergence, creativity, and progressive development in nature. The hard problem of consciousness, explaining why there's subjective experience at all, remains one of the deepest challenges to a purely physicalist worldview. Some philosophers argue that consciousness will eventually be explained in purely physical terms, while others contend that consciousness represents a fundamental feature of reality that cannot be reduced to matter and energy alone. The possibility that consciousness is basic to the universe, like mass or charge, opens up new ways of thinking about the relationship between mind and cosmos. As these scientific discoveries continue to unfold, they create space for new forms of philosophical thinking that transcend traditional categories. Process philosophy, which emphasizes becoming over being, resonates with quantum mechanics and cosmological evolution. Information-based approaches to reality connect with quantum information theory and the holographic principle. Panpsychist theories, which attribute some form of consciousness to all matter, gain new plausibility from quantum mechanics and integrated information theory. The philosophical implications of modern physics extend beyond abstract metaphysics to practical questions about how we should live. If consciousness participates in creating reality, then our thoughts and observations carry greater responsibility. If everything is interconnected through quantum entanglement, then our actions ripple through the fabric of existence in ways we might not fully comprehend. If we exist in a multiverse of infinite possibilities, then perhaps our task is not to achieve some predetermined goal, but to explore and express the unique possibilities available to us in this particular branch of reality. Tonight, as you rest in contemplation of these profound questions, remember that philosophy and physics together point toward a universe far more mysterious, interconnected, and alive with possibility than our ancestors ever imagined. The questions that have puzzled humanity for millennia remain vital and relevant, enriched rather than answered by our growing scientific understanding. Your existence as a conscious being capable of contemplating these mysteries is itself perhaps the most remarkable fact we encounter. A universe knowing itself through the miracle of awareness. Let these deep questions carry you gently into sleep, knowing that to live in such a mysterious and beautiful cosmos is itself a privilege beyond measure. Whether reality is fundamentally mental or physical, deterministic or free, singular or multiple, your capacity for wonder and reflection connects you to the deepest truths of existence itself. Let your mind drift now into the vast, invisible architecture of our cosmos, the mysterious dark matter and dark energy that together comprise an astounding 95% of everything that exists, yet remain among the universe's deepest secrets. As you settle into the gentle embrace of night, imagine floating through space filled not just with the familiar glow of stars and galaxies, but with an invisible cosmic web of dark matter threading through every corner of existence, while dark energy quietly drives the accelerating expansion of space itself. Tonight, we'll explore these hidden forces that shape the very structure of space-time on the grandest scales, discovering how the universe is far more mysterious and dynamic than the visible cosmos suggests. Close your eyes and picture the night sky as you know it, scattered with points of starlight, painted with the soft glow of distant galaxies, marked by the gentle arc of the Milky Way. This beautiful tapestry represents everything humanity could see and study for most of our history, yet it accounts for only about 5% of the universe's total content. The remaining 95% exists in forms so elusive that we can detect them only through their gravitational effects. Invisible players in the cosmic drama whose presence is felt everywhere, but whose nature remains tantalizingly mysterious. Dark matter makes up approximately 27% of the universe, outweighing ordinary matter by more than 5 to 1. This invisible substance doesn't emit, absorb, or reflect light in any way we can detect, earning its name from this apparent darkness. Yet dark matter's gravitational influence shapes every large-scale structure in the cosmos. The galaxies that wheel slowly through space, including our own Milky Way, are embedded within vast halos of dark matter that extend far beyond their visible boundaries. Without dark matter's gravitational scaffolding, galaxies would fly apart, their stars scattered into the void by the centrifugal forces of rotation. The discovery of dark matter began with astronomer Vera Rubin's careful observations of galactic rotation curves in the 1970s. She found that stars in the outer regions of galaxies move much faster than they should, if only visible matter were providing the gravitational force to hold them in orbit. According to the laws of gravity, these outer stars should either slow down dramatically or be flung out of their galaxies entirely. Yet there they were, orbiting at speeds that suggested the presence of much more mass than could be accounted for by visible stars, gas, and dust. This led to the realization that each galaxy sits within a vast halo of invisible matter, creating the gravitational environment necessary to explain the observed motions. Computer simulations of cosmic evolution show that without dark matter, the universe would look entirely different. A smooth, nearly featureless expanse with little of the rich structure we observe today. Dark matter acts as the cosmic web upon which visible matter hangs, providing the gravitational seeds around which gas can condense to form the first stars and galaxies. The nature of dark matter particles remains one of the greatest mysteries in physics. They must be something entirely different from ordinary atoms. Particles that interact through gravity, but barely, if at all, through the electromagnetic, weak, or strong nuclear forces. Leading candidates include hypothetical particles, like WIMPs, weakly interacting massive particles, or axions, exotic remnants from the early universe that could fill space with invisible mass. Deep underground detectors around the world listen carefully for the rare occasions when these dark matter particles might interact with ordinary matter, hoping to catch direct evidence of their presence. Even more mysterious is dark energy, comprising about 68% of the universe and driving its accelerating expansion. When Einstein first developed his equations of general relativity, he added a cosmological constant, a form of energy inherent in space itself, to keep the universe static, as he believed it should be. When astronomical observations later showed that the universe was expanding, Einstein reportedly called the cosmological constant his greatest mistake. But in the 1990s, observations of distant supernovae revealed something even more surprising. The universe's expansion is not slowing down due to gravity, as expected, but is actually accelerating. This acceleration requires a form of energy that acts opposite to gravity, pushing space apart rather than pulling matter together. Dark energy appears to be a property of space itself. The more space expands, the more dark energy comes into existence, driving ever faster expansion. Unlike dark matter, which clumps together gravitationally to form the cosmic web, dark energy remains uniformly distributed throughout space, maintaining a constant density even as the universe grows larger. The implications of dark energy are profound and unsettling. If its influence continues to dominate, the universe will expand exponentially, eventually carrying every galaxy beyond the horizon of every other galaxy. Stars will exhaust their fuel. Black holes will evaporate through Hawking radiation, and the cosmos will fade into a cold, empty darkness, punctuated only by the occasional quantum fluctuation. This scenario, known as the heat death of the universe, represents the ultimate victory of entropy over structure, of expansion over gravity. Yet the true nature of dark energy remains deeply puzzling. The cosmological constant interpretation suggests that empty space itself possesses energy, but quantum field theory calculations of vacuum energy give results that are wrong by a factor of 10 to the power of 120, perhaps the largest discrepancy between theory and observation in the history of science. Alternative theories propose that dark energy might be a dynamic field called quintessence, which could change over time, or that our understanding of gravity itself might need modification on cosmic scales. The interplay between dark matter and dark energy has shaped cosmic evolution from the earliest moments after the Big Bang. In the universe's youth, when everything was much closer together, dark matter's gravitational attraction dominated over dark energy's repulsion. This allowed cosmic structure to form. Dark matter halos condensed from tiny quantum fluctuations, providing the gravitational wells into which ordinary matter could fall to form the first stars and galaxies. But as the universe expanded and dark matter became more dilute, dark energy's influence grew stronger, eventually taking control of cosmic expansion and preventing the formation of new large-scale structures. Recent observations have revealed the cosmic web in unprecedented detail, a vast network of dark matter filaments connecting galaxy clusters across billions of light years, with enormous voids between them where little matter exists. This web-like structure emerged from the interplay of dark matter's gravity and dark energy's expansion, creating the scaffolding upon which all visible cosmic architecture hangs. Your own existence depends on this invisible framework, as the atoms in your body were forged in stars that formed within dark matter halos billions of years ago. The search for dark matter continues through multiple approaches. Particle physicists use powerful accelerators to try to create dark matter particles in high-energy collisions. Astronomers map the gravitational lensing effects of dark matter halos, watching how they bend, and distort the light from background galaxies. Space-based telescopes measure the cosmic microwave background radiation, searching for the subtle fingerprints of dark matter interactions in the early universe. Each approach provides pieces of the puzzle, slowly constraining the properties these invisible particles must possess. Similarly, the study of dark energy involves mapping the expansion history of the universe with ever greater precision. By observing supernovae, baryon acoustic oscillations, and the growth of cosmic structure over time, astronomers hope to determine whether dark energy's strength has remained constant or changed as the universe evolved. This could distinguish between different theoretical models and provide clues about the fundamental physics underlying cosmic acceleration. The philosophical implications of dark matter and dark energy are as profound as their physical effects. They remind us that our understanding of reality remains profoundly incomplete, that the universe is far stranger and more mysterious than our everyday experience suggests. The humility required to acknowledge that 95% of existence remains hidden from us mirrors the ancient philosophical recognition of the limits of human knowledge and the vastness of what remains unknown. Yet there's something deeply beautiful in the way these invisible components work together to create the visible universe we know and love. Dark matter provides the gravitational scaffolding for cosmic structure, while dark energy ensures that space continues to expand, preventing gravitational collapse and allowing new possibilities to emerge. Together, they create a dynamic cosmic environment where complexity, structure, and consciousness can evolve and flourish, even if only temporarily, on cosmic timescales. Tonight, as you drift into peaceful sleep, remember that you're surrounded by this invisible cosmic ocean. Dark matter particles might be streaming through your body right now, mostly unnoticed, but occasionally leaving the faintest trace of their passage. The space around you is infused with dark energy, gently pushing the boundaries of the universe ever outward. You rest within a cosmos that is 95% mystery, a universe whose visible beauty represents just the smallest fraction of a much vaster, stranger, and more wonderful reality. Let these thoughts of cosmic mystery carry you into dreams, knowing that to exist in such a universe, where the invisible outweighs the visible by 20 to 1, where the very fabric of space pulses with mysterious energy, is to participate in the greatest adventure of discovery ever undertaken. Rest peacefully in the knowledge that mystery and wonder surround you always, woven into the very structure of space-time itself. Let your thoughts drift now toward the distant future, billions upon billions of years from now, as we explore the ultimate destiny of space and time themselves. Tonight, as you settle into the deepest comfort and prepare for peaceful sleep, we'll journey to the very edges of possibility, discovering what cutting-edge physics reveals about the fate of stars, galaxies, black holes, and the fabric of reality itself. This is our final voyage together through the cosmos, a gentle expedition into tomorrow's tomorrows, where we'll see how the universe might end, how time itself could cease to flow, and what profound mysteries await in the far reaches of eternity. Close your eyes and imagine the Earth as it will be in about 5 billion years, when our sun begins to exhaust the hydrogen fuel in its core. The gentle star that has warmed our planet for so long will start to expand into a red giant, growing so large that it might engulf the inner planets entirely. But long before that happens, The increasing solar luminosity will have boiled away Earth's oceans and stripped away its atmosphere, leaving behind a barren world bathed in the fierce light of a dying star. This transformation, dramatic as it sounds, represents just the first movement in a cosmic symphony that will play out over timescales so vast they challenge human comprehension. As we drift forward through deep time, imagine the Milky Way and Andromeda galaxies beginning their slow-motion collision, an event scheduled to occur in about 4.5 billion years. Despite containing hundreds of billions of stars each, these galaxies will merge with surprisingly little violence. The vast distances between stars mean that actual stellar collisions will be rare. Instead, gravitational forces will rearrange the orbits of stars and solar systems, creating a new, larger galaxy that astronomers have playfully named Milkomeda. The night sky of any surviving worlds will be transformed, painted with unfamiliar constellations and filled with the magnificent spiral arms of this cosmic union. But even this galactic merger is a local event compared to the grander changes occurring throughout the universe. Dark energy continues to drive the acceleration of cosmic expansion, pushing galaxy clusters farther and farther apart. In about 100 billion years, the observable universe will have expanded so much that galaxies beyond our local group will have moved beyond our cosmic horizon, their light redshifted to infinite wavelengths and effectively disappearing from view. Any astronomers living in that distant epoch will see a much lonelier universe, one that appears to contain only their own local cluster of galaxies surrounded by an endless, empty darkness. As we journey even further into the future, approaching the era that physicists call the stelliferous age, the time when stars still burn and light the cosmos, we witness the gradual exhaustion of the universe's capacity for star formation. The gas and dust that fuel stellar birth become increasingly dilute as the universe expands, and heavier elements created in stellar cores become locked away in white dwarfs, neutron stars, and black holes. By about 1 trillion years from now, the last stars will flicker out, leaving the universe populated mainly by the slowly cooling remnants of stellar death. Yet even in this darkening cosmos, processes continue on timescales that dwarf the current age of the universe. Brown dwarfs, failed stars too small to sustain nuclear fusion, will continue to cool and fade over hundreds of trillions of years. White dwarf stars, the dense cores of dead stars like our sun will become, will gradually radiate away their remaining heat, transforming into cold, dark crystals of carbon and oxygen floating through space. Neutron stars will slow their rapid rotation, and their magnetic fields will decay, leaving behind dark, silent spheres of matter compressed to nuclear density. The universe enters what cosmologists call the degenerate era, dominated by protons, neutrons, electrons, and neutrinos. But even these seemingly stable particles may not be eternal. Some theories suggest that protons themselves might decay, with half-lives of perhaps 10 to the 34th power years, a timescale so vast that it makes the current age of the universe seem like a brief moment. If protons do decay, then all atomic matter will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an ever-expanding, ever-cooling cosmos. During this unimaginably distant epoch, black holes become the dominant gravitational structures in the universe. But even these cosmic monsters are not immortal. Stephen Hawking's calculations show that black holes slowly evaporate by emitting radiation, with smaller black holes disappearing faster than larger ones. A black hole with the mass of our Sun would take about 10 to the 67th power years to completely evaporate, a number so large that writing it out would require more digits than there are atoms in the observable universe. The supermassive black holes that lurk in the centers of galaxies will persist even longer, some taking 10 to the power of 100 years or more to fade away completely. As these last black holes evaporate through Hawking radiation, they leave behind only elementary particles and photons in a universe that has become unimaginably cold and dilute. The temperature approaches absolute zero, and the density approaches zero as well, creating a cosmos that is essentially empty except for occasional particles separated by distances larger than our current observable universe. Yet even in this seemingly barren state, quantum mechanics ensures that the universe retains a subtle vitality. Virtual particle pairs continuously appear and disappear in the quantum vacuum, and rare quantum tunneling events might occasionally create new structures or even new universes. Some theoretical possibilities offer hope for renewal even in this distant future. Quantum fluctuations might occasionally create regions of low entropy that could serve as seeds for new complexity. If proton decay occurs, the resulting energy release might drive processes that create new forms of organization. Most speculatively, random quantum fluctuations might eventually recreate any possible arrangement of matter and energy, including conscious observers like ourselves. Though the waiting times involved would be beyond astronomical, the question of whether time itself has an ultimate fate remains one of the deepest mysteries in physics. If the universe continues, expanding forever, driven by dark energy, then time might stretch on eternally, marking the gradual approach to maximum entropy and minimum temperature. But some theories suggest alternative scenarios. If dark energy strength changes over time, cosmic expansion might eventually reverse, leading to a big crunch that returns the universe to a state similar to its beginning. Other models propose cyclic cosmologies where the universe undergoes endless cycles of expansion and contraction, with each cycle potentially creating new physical laws and constants. The developing theory of quantum gravity might reveal even stranger possibilities for the fate of spacetime. Some approaches suggest that space and time themselves might be emergent properties of more fundamental quantum processes. If so, the evolution of the universe might eventually lead to the breakdown of spacetime as we understand it, replaced by new forms of existence that we cannot yet imagine. The fabric of reality itself might undergo phase transitions, like water freezing into ice, creating new physics and new possibilities for structure and consciousness. Recent discoveries in cosmology and fundamental physics continue to reshape our understanding of cosmic destiny. The measurement of gravitational waves from colliding black holes and neutron stars provides new insights into the extreme physics that will dominate the universe's far future. Studies of dark energy and dark matter might reveal whether these mysterious components will continue to drive cosmic evolution or undergo changes that could alter the universe's ultimate fate. Perhaps most remarkably, the possibility of life and intelligence persisting into the far future remains an open question. While biological life, as we know it, seems unlikely to survive the heat death of stars, other forms of information processing and consciousness might be possible. Digital civilizations might find ways to harness the slow decay of black holes or the rare energy releases from proton decay. Consciousness itself might evolve into forms we cannot currently imagine, perhaps existing as pure information patterns that persist even as matter and energy become ever more dilute. The search for a theory of quantum gravity promises to reveal new insights about the nature of space, time, and existence itself. String theory, loop quantum gravity, and other approaches might show us that reality has even more dimensions and possibilities than we currently recognize. The ultimate fate of space and time might be not ending, but transformation, a metamorphosis into new forms of existence that transcend our current understanding of what it means to be. Tonight, as you drift into peaceful sleep, carry with you the wonder of existing in a universe with such a vast and mysterious future ahead of it. Your consciousness, your capacity for thought and dream, participates in cosmic processes that will unfold over timescales beyond imagination. You are part of a universe that began in quantum creativity and will continue evolving in ways we are only beginning to glimpse. Rest peacefully in the knowledge that to live in such a cosmos, where space and time themselves might be just the beginning of even grander realities, is the greatest privilege existence can offer. If you've enjoyed this journey through the deepest mysteries of space and time, if these explorations of cosmic wonder have sparked your curiosity and brought you moments of peaceful contemplation, then please subscribe to the Sleepy Cosmos for more gentle voyages into the universe's most profound secrets. Like this video if it's helped you drift toward restful sleep while expanding your understanding of reality, and let me know in the comments what cosmic mysteries you'd like us to explore together next. Sweet dreams, fellow travelers, and remember that even as you sleep, you remain part of the eternal dance of space, time, and consciousness that makes existence the most beautiful mystery of all.